Chemical Building Blocks, Chapter 1, Intro to Matter, Section 2, Measuring Matter. Here's a riddle for you. Which weighs more, a pound of feathers or a pound of sand? If you answered a pound of sand, think again. Both weigh exactly the same, 1 pound. There are all sorts of ways to measure matter, and you use these measurements every day. Scientists rely on measurements as well. In fact, scientists work hard to make sure their measurements are as accurate as possible. Weight and mass. Suppose you want to measure your weight. To find the weight, you step on a scale like the one shown in Figure 11. Your body weight presses down on the springs inside the scale. The more you weigh, the more the springs compress, causing the pointer on the scale to turn farther, giving a higher reading. However, your scale would not indicate the same weight if you took it to the moon and stepped on it. You weigh less on the moon, so the springs of the scale would not be compressed as much by your weight. Your weight is a measure of the force of gravity. Gravity on you. On Earth, all objects are attracted toward the center of the planet by the force of Earth's gravity. On another planet, the force of gravity on you may be more or less than it is on Earth. On the moon, you would weigh only about 1/6 of your weight on Earth. Mass. Why do you weigh less on the moon than on Earth? The force of gravity depends partly on the mass of an object. The mass of an object is the measurement of the amount of matter in the sub-object. If you travel to the moon, the amount of matter in your body, all your mass, does not change, but the mass of the moon is much less than the mass of the Earth, so the moon exerts much less gravitational force on you. Unlike weight, mass does not change with location, even when the force of gravity on an object changes. For this reason, scientists prefer to measure matter by its mass rather than its weight. The mass of an object is a physical property. Units of mass. To measure the properties of matter, scientists use a system called the International System of Units. This system is abbreviated SI after its French name, Système International. The SI unit of mass is the kilogram, or kg. If you weigh 90 pounds on Earth, your mass is about 40 kilograms. Although you will see kilograms used in this textbook, usually you will see a smaller unit, the gram, or G. There are exactly 1,000 grams in a kilogram. A nickel has a mass of 5 grams, and a baseball has a mass of about 150 grams. Volume. You learned in Section 1 that all matter has mass and takes up space. The amount of space that matter occupies is called its volume. It's easy to see that solids and liquids take up space. Gases have volume too. Watch a balloon as you blow into it. You're actually increasing the volume of gas in the balloon with your breath. Units of volume. Common units of volume include the liter, milliliter, and cubic centimeter. Some plastic soda bottles hold 1 liter of liquid. Volumes smaller than a liter are usually given in milliliters. A milliliter is 1/1000th of a liter and is exactly the same volume as 1 cubic centimeter. A teaspoon full of water has a volume of about 5 milliliters, and an ordinary can of soda contains 355 milliliters of liquid. In a laboratory, volumes of liquids are usually measured with a graduated cylinder. Calculating volume. The volumes of solid objects are usually expressed in cubic centimeters. Suppose you want to know the volume of a rectangular object, such as the brick shown in Figure 13. First, you measure the brick's length, width, and height, or thickness. Then you multiply these values. Volume equals length times width times height. Measurements always have units, so when you multiply the 3 measurements, you must multiply the units as well as the numbers. So the units equal centimeter times centimeter times centimeter, which is centimeter to the 3rd power, or centimeters cubed. How can you measure the volume of an irregular object, such as a piece of fruit or a rock? One way is to submerge the object in water in a graduated cylinder. The water level will rise by the amount that is equal to the volume of the object in milliliters. Density. Samples of 2 different materials may have the same volume, but they don't necessarily have the same mass. Remember the riddle about the sand and the feathers? A kilogram of sand takes up much less space than a kilogram of feathers. The volumes differ because sand and feathers have different densities, an important property of matter. Density relates the mass of a material in a given volume. Often, density is expressed as a number of grams in 1 cubic centimeter. For example, the density of water at room temperature is stated as 1 gram per cubic centimeter, or 1 g over centimeter cubed. This value means that every gram of water has a volume of 1 centimeter cubed. Notice that the word per is replaced by the fraction bar in the units of density. The bar tells you that you can determine the density of a sample of matter by dividing its mass by its volume. So, density equals mass divided by volume. Sinking or floating. Suppose you have a solid block of wood and a solid block of iron. When you drop both blocks into a tub of water, you can see right away that the wood floats and the iron sinks. You know that the density of water is 1 gram per centimeters cubed. Objects with densities greater than that of water will sink. Objects with lesser densities will float. So the density of this wood is less than 1 gram per centimeters cubed. The density of the iron is greater than 1 gram per centimeters cubed. Watch a bottle of oil and vinegar salad dressing after it's been shaken. You will see oil droplets rising above the vinegar. Finally, the oil will form a separate layer above the vinegar. What can you conclude? Well, you're right if you said that the oil is less dense than the vinegar. Using density. Density is a physical property of a substance, so density can be used to identify an unknown substance. For example, suppose you were hiking in the mountains and found a shiny golden colored rock. How would you know if the rock was really gold? Later at home, you could look up the density of gold at room temperature, then measure the mass and volume of the rock and find its density. If the two densities match, you would have quite a find.